Here we want to investigate the question, what is an integral? And before we even use that terminology in Calc 1, we introduce it by explaining that we want to find the area under the curve. So when we're considering a definite integral, that is defined to be the area under the curve. So when computing the definite integral, what we're really looking for is what is the area under the curve. So let's suppose we had a picture like this. That's my y equals f of x. And what we want to do is compute the integral from a to b of f of x dx. Then what we're looking for is this area under here. Now the shape we're computing the area of isn't a natural shape from geometry that we have any sort of formula for. So in order to get the shape, what we do is we break this area up into many little areas, and we approximate those using rectangles. So here we go, this strip right here. So that interval to a to b, we break into n subintervals of equal length. Now that length from a to b has the length b to minus a, and since I'm making n of them, this length is b minus a over n, which we denote by delta x. So we'll take a look at the ith subinterval, which will have subscripts xi minus 1 and xi. We end at n, so b is x sub n, and a is x sub 0. Now each strip we want to approximate using some sort of rectangle. We could use where the right endpoint hits the curve as my height, and I would have this rectangle right here. So then the area of the ith strip using right endpoints would be delta x times f of xi. That f of xi is the height, right? Because we've made a rectangle, so we take width, that's my delta x, times height. Now I want to add all of those up for an approximation of the total area. So the total area under that curve from a to b is approximately the sum I equals 1 to n of delta x times f of xi. As we saw on the last slide, if we're trying to approximate the area under this curve, y equals f of x from a to b, and if we use right endpoints to determine the height of the rectangles we use for approximation, like this here, then we see that the integral from a to b of f of x dx, which is the exact area under the curve, that's going to be approximately the sum I equals 1 to n for the number of rectangles whose areas that we're adding up, of delta x, which is the width of the rectangle, times f of xi, which is up here, is exactly how we got the height of the rectangle. We could do the same thing. We could build rectangles using left endpoints. So I would go up to that ith interval, and I would look at xi minus 1 to get the height. And instead I would have this rectangle right here, and I would be using that area in my approximation. So my integral from a to b of f of x dx is approximately the sum I equals 1 to n of delta x for the width, and now the height of this rectangle is determined by that endpoint xi minus 1. So the height is f of xi minus 1. Now, we could actually use any point in that interval to get the height of the rectangle. So for example, we'll just pick some special number in between xi star and xi, and we'll call it xi star to denote any random number or point between xi minus 1 and xi. And I use that, and I go up and find out where that hits the curve. Up here. And that hits the curve at f of xi star. And that's what we've used for the height. So using any point, any sample point, and you could use the left endpoint or the right endpoint or anything in between. So using sample points, we can see that the integral from a to b, so again that exact area under f of x between a and b, will be approximately equal to the sum I equals 1 to n of delta x times f of xi star. So from the last slide, we saw that the integral from a to b of f of x dx is approximately the sum I equals 1 to n of delta x times f of xi star. Since the xi star is any sample point, it could be a left endpoint or a right endpoint, and so it's perfectly fine to use that as a condensed way of saying all the things we said on the last slide. So the question is, how do we get a better approximation? This happens when we take larger n's. So if we divide that interval up into more and more and more subintervals, if we make these rectangles even smaller and smaller, we'll get better approximations. So the smaller that width is, the smaller delta x is, the better our approximation will be for the exact area. So what we want to do ideally is take n to be as large as it can be, but I can always keep putting more rectangles in there. So what we're really doing is taking a limit. So what we have in the end is that the integral from a to b of f of x dx is exactly equal to the limit as n goes to infinity, so more and more and more rectangles, of that sum I equals 1 to n of delta x times f of xi star. And this is how we can compute the definite integral. For more information on the indefinite integral, you should see the video that compares the two ideas of indefinite integral versus definite integral.